Welcome back to the School of Joy.
Oh, I like that.
Today, we're tackling a subject that might give you some high school flashbacks.
Uh-oh.
Calculus.
Calculus.
But trust me,
Okay.
we're going to make it way more fun than those dusty textbooks.
I'm all for that.
You wanted to explore calculus more deeply, so we've got a stack of sources to unpack. From, ancient Greek paradoxes
Oh, wow.
to the mind-bending work of Newton and Leibniz.
Those are some big names.
By the end of this deep dive, you'll see how calculus isn't just about formulas.
Right.
It's a language to understand the world's hidden patterns.
Exactly. It's about understanding change, time, space, emotion, all those things we experience every day.
Okay, let's kick things off with a classic brain tease.
Love those.
Zeno's paradox.
Okay.
You know, the one where you have to cross half the distance to reach a wall,
Right.
then half of that remaining distance,
Uh-huh.
and so on infinitely.
It seems impossible.
It seems like you'd never actually reach the wall.
Yeah.
I actually used to use this paradox to justify not cleaning my room.
Oh, clever.
It takes forever, right?
Well, it does seem impossible.
Mm-hmm.
But that's where the concept of limits comes in. Think of it like this.
Okay.
Imagine dividing a cake in half,
Okay.
then half again, and so on. You're getting closer and closer to having nothing left.
Right.
But you never actually reach zero.
Right. You're always left with a tiny sliver no matter how many times you divide it.
Exactly. But the limit of this infinite process of dividing the cake is actually zero. Even though you can't physically divide it into nothing, the concept of a limit allows us to grasp what happens as we approach an entity, and it's this idea that helps us solve Zeno's paradox.
So we can reach the wall
Yes.
because those infinitely small steps add up to a finite distance. That's pretty mind-blowing.
It is, and this leads us to the creation of the real numbers.
Okay.
A system that includes not just whole numbers and fractions, but also those mind-boggling irrational numbers, like pi and the square root of 2, which can't be expressed as simple fractions.
The real numbers.
Yep.
The whole gang's here. But how do they help us make sense of the real world?
That's where functions come in. They allow us to see how one thing depends on another.
Okay.
Think about something like the temperature outside. The temperature is a function of the time of day.
Okay, so the input is the time of day and the output is the temperature.
Exactly. Functions create powerful connections between quantities, and they're used to model relationships between all sorts of things. For instance, in physics, Galileo's law of falling objects expresses the distance an object falls as a function of time.
I vaguely remember that from physics class. Something about objects falling at the same rate regardless of their weight.
That's right. But the key here is that we can use this function to precisely calculate how far an object has fallen if we know how long it's been falling.
So functions are like little mathematical machines that take an input and spit out an output. And this could be applied to way more than just falling objects.
Absolutely. The versatility of functions is amazing. They can be used to model relationships between temperature and pressure, supply and demand,
Wow.
even population growth over time. Basically, anywhere you see a relationship where one thing depends on another, there's likely a function at work.
Okay, I'm starting to see how functions help us describe change. But how does calculus tackle the concept of speed at a single moment?
Oh, yes.
What we call instantaneous speed. Like, how fast is a falling object going at the exact moment the clock hits 1 second? That seems impossible to measure.
It might seem impossible.
Yeah.
But that's where one of the fundamental tools of calculus comes in. The derivative.
Okay, so the derivative captures the rating change at a specific point.
Exactly. It's not about the average speed over a period of time,
Right.
but the speed at a precise instant. Visually, you can think of the derivative as the slope of a line that just touches the curve of a function at a single point.
Okay.
That slope represents how much the function is changing at that exact moment.
So if the slope is steep, the function is changing rapidly.
Right.
And if it's flat, the function is changing slowly or not at all.
Exactly.
So it's like a speedometer reading for a function at any given point.
Exactly. But here's the cool part.
Yeah.
The derivative isn't just limited to speed.
Oh.
It can describe any kind of instantaneous change, the growth rate of bacteria, the rate of a chemical reaction,
Wow.
the rate of change in stock prices. It's a fundamental tool in countless fields.
Wow, derivatives sound pretty powerful.
They are.
It's like a secret decoder wing for understanding change in all sorts of areas. But what about area? Like, how do we calculate how much space a curved shape takes up? That seems impossible to measure accurately.
You're right. It's a different concept.
Yeah.
And that's where integral calculus comes to the rescue.
Integrals.
Yes.
Aren't those squiggly S-shaped symbols? They always looked a bit intimidating.
That's the one. They might look intimidating. But the idea behind them is pretty clever. Imagine dividing the area under the curve into a bunch of tiny rectangles.
Okay, I'm picturing it. We can calculate the area of each rectangle.
Yes.
Just base times height. So we add up the areas of all these little rectangles to get a rough estimate of the area under the curve.
Exactly. And here's where it gets really cool.
Okay.
As you make those rectangles smaller and smaller, your approximation gets more and more accurate. It's like using increasingly finer-grained building blocks to create a more detailed model of the area. The limit on this process, where the rectangles become infinitely small, is what we call the definite integral,
Okay.
which gives us the precise area under the curve.
That's amazing. It's like using simple shapes to solve a complex problem. It reminds me of those Lego blocks.
Yes.
Use enough of them, and you could build almost anything.
That's a great analogy.
So we've got derivative for understanding instantaneous change.
Yeah.
And integrals for calculating areas. But they seem like totally separate concepts.
They do, don't they?
Yeah.
But that's what's so fascinating about calculus. There's a mind-blowing connection between these two seemingly unrelated ideas.
Okay, I'm intrigued. Tell me more about this connection.
It's called the fundamental theorem of calculus.
Okay.
And it's one of the most important theorems in mathematics. It basically links the two worlds of derivatives and integrals.
Wow, a mathematical plot twist. I'm on the edge of my seat. What does this fundamental theorem actually tell us?
Well, it has two parts. The first part says that if we know the rate of change of a quantity,
Okay.
its derivative,
Uh-huh.
we can figure out the total change over an interval using integration. It's like knowing the speed of a car and using that to calculate how far it traveled over a certain time.
Okay, that makes sense. So the first part tells us we can use integration to find the total change if we know the rate of change. What about the second part?
The second part reveals a deeper connection. It says that there's a link between finding the area under a curve,
Okay.
that definite integral we talked about,
Yeah.
and finding a function whose derivative matches that curve,
Okay.
what we call the antiderivative.
Wait, so finding the area under a curve is somehow related to finding a function's antiderivative. How is that even possible?
It's a bit like a mathematical magic trick, but it has profound implications. Essentially, it means that integration and differentiation are inverse processes. We can use integration to solve problems about rates of change and vice versa. This connection revolutionized mathematics and physics. For example, it means you can predict a rocket's position in space just by knowing its acceleration, which is pretty mind-blowing.
Okay, that is mind-blowing. But the fundamental theorem is this incredible bridge connecting these two separate continents of mathematical ideas.
Exactly.
Wow.
And it gave us incredibly powerful tools for modeling and understanding the world around us.
This has been an incredible journey so far.
I agree.
From ancient paradoxes to mind-blowing theorems, it's like calculus is opening up a whole new way of looking at the world.
Absolutely. And remember, we're still just scratching the surface. Calculus has vast applications in fields like physics, engineering, economics, even biology.
Hold on, before you unleash everyone on unsuspecting textbooks, let's dive a bit deeper into how calculus actually tackles these real-world problems. Remember those infinitely small changes we talked about with derivatives?
Uh-huh.
They sound a bit fuzzy to me, to be honest.
Okay.
Like, how can something be infinitely small but still exist?
You're hitting on a point that caused a lot of debate for mathematicians for centuries.
Oh, really?
The concept of infinitesimals,
Okay.
those infinitely small quantities, was a bit of a headache.
Yeah.
Even for the brilliant minds of Newton and Leibniz who helped develop calculus.
So mathematicians were wrestling with the idea of something being smaller than any imaginable number,
Yeah.
but not actually zero. That sounds like a recipe for a brain meltdown.
It did cause some meltdowns. Even Newton and Leibniz struggled to give a rigorous definition of infinitesimals.
Wow, and those guys practically invented calculus.
It's true.
So how did they resolve this crisis of infinitely small proportions?
It took a while, but in the 19th century, mathematicians like Cauchy and Weierstrass came to the rescue.
Oh, good.
They developed a more rigorous foundation for calculus based on the concept of limits, which we talked about earlier.
Ah, limits to the rescue again. So instead of relying on these mysterious infinitesimals, they used limits to define derivatives and integrals in a more solid way.
Exactly. It's like building a solid foundation for a skyscraper instead of balancing it on stilts. They showed that we could avoid those slippery infinitesimals by defining derivatives and integrals in terms of limits of ordinary numbers.
That makes sense. A solid foundation built on limits sounds much safer than shaky infinitesimals. But this whole idea of limits is still a bit abstract. Can you give me a real-world example of how it works, besides that cake we were dividing earlier?
Sure. Let's go back to Zeno's paradox of crossing a room.
Okay.
Remember, we said that the limit of that infinite process of having distances is actually the full distance of the room.
Right. We can reach the other side because those infinitely small steps add up to a finite distance.
Yes.
It's like those steps are getting so tiny that they eventually become indistinguishable from a smooth, continuous motion.
That's the power of limits. They allow us to understand the behavior of a process as it approaches infinity, even if we can't actually reach infinity.
So limits are like a mathematical bridge between the finite and the infinite. They let us peek into the realm of the infinite without getting lost in the abyss.
That's a beautiful way to put it. And this brings us to the concept of continuity in calculus, which is all about how smoothly a function behaves.
Okay.
A continuous function is like a roller coaster gliding effortlessly along its track. No sudden jumps, breaks, or holes. It's all connected, flowing seamlessly.
But functions can be discontinuous too, right?
Absolutely.
Like a roller coaster that suddenly drops or has a gap in the track.
Absolutely. Functions can have all sorts of interesting behaviors.
Oh.
Jumps, breaks, even wild oscillations. But understanding continuity is crucial for many of the theorems and applications of calculus.
Okay, so continuity is like a smoothness check for functions. But why should we care? What's the big deal about a function being continuous?
Well, many of the key theorems in calculus, like the mean value theorem,
Okay.
only work for continuous functions.
So continuity is like a VIP pass to the exclusive club of calculus theorems. But seriously, why is it so important for these theorems?
It reflects a fundamental aspect of how we experience the world. Think about how we perceive time or motion. We don't experience time as a series of disconnected jumps or snapshots. We feel it as a continuous flow, a smooth transition from one moment to the next. Similarly, we see motion as a continuous progression, not a series of jerky starts and stops.
I get it. Continuity captures that sense of flow and interconnectedness that we feel in the world around us. It's the glue that holds our experience together.
Beautifully put. And calculus gives us a language to describe and analyze this continuity. Which brings us to one of the most elegant and powerful theorems in calculus,
Okay.
the mean value theorem.
Okay, tell me about this mean value theorem. Does it involve calculating the average value of something?
You're on the right track. The mean value theorem is all about connecting average change to instantaneous change. It's a bit like a mathematical detective story, revealing a hidden connection between two seemingly different aspects of a function.
Intriguing. So, how does this mathematical detective work unravel the mystery?
Imagine you're driving from one city to another.
Okay.
You know, the distance between the cities and the time it took you to get there?
Uh-huh.
You can easily calculate your average speed,
Right.
just distance divided by time.
Right. Basic road trip math.
Now, the mean value theorem says that at some point during a trip, your instantaneous speed must have been exactly equal to your average speed.
Wait, really? So even if I was speeding or driving slowly at different parts of the trip, at some point my speedometer must have shown my exact average speed?
That's what the theorem guarantees. It might seem obvious, but it has profound implications. It means that there's always a connection between the overall behavior of a function and its behavior at specific points.
That's pretty neat. So this seemingly simple theorem reveals a deep connection between the average and the instantaneous. But how do we actually prove this mean value theorem? Does it involve complicated formulas or abstract reasoning?
The proof is actually quite elegant and insightful and relies on a combination of geometric and algebraic ideas.
Okay.
It starts with a simpler theorem called Rolle's theorem.
Rolle, was he one of those mathematicians who initially doubted the whole idea of calculus?
He was. Ironically, Rolle was a critic of calculus, even though his theorem became a key stepping stone in the development of the mean value theorem.
That's funny. It's like those musicians who write a hit song they secretly hate. So what does this Rolle's theorem say?
Rolle's theorem states that if you have a continuous function that starts and ends at the same value, then somewhere in between, its derivative must be zero.
Okay, let me visualize this. So if I draw a smooth curve that starts and ends at the same height, there must be at least one point on the curve where the tangent line is horizontal.
Exactly. It's like that roller coaster again.
Oh, yeah.
If it starts and ends at the same height, there must be at least one point where it levels off, even for a brief moment.
I see. And this leveling off point is where the derivative is zero, because the slope of a horizontal line is zero, right?
Precisely. Now, the mean value theorem is essentially a tilted version of Rolle's theorem.
A tilted version. How do you tilt a theorem?
Imagine taking that roller coaster track from Rolle's theorem and tilting it at an angle.
So instead of starting and ending at the same height, now the curve starts and ends at different heights.
That's right. And instead of looking for a point where the tangent line is horizontal,
Okay.
we're looking for a point where the tangent line is parallel to the secant line connecting the starting and ending points of the curve.
Now, what's a secant line again, just to refresh my memory?
A secant line is simply a line that cuts through a curve,
Okay.
connecting 2 points on that curve.
Right, got it. So the mean value theorem guarantees that there's always at least one point on the curve where the tangent line has the same slope as that secant line connecting the start and end points.
Yes, it's like saying that even on a tilted roller coaster, there's at least one point where the instantaneous slope of the track matches the average slope over the whole ride.
Okay, that makes sense. I'm starting to grasp the elegance of this theorem. But what makes it so powerful? Why do mathematicians get so excited about it?
The mean value theorem is powerful because it acts as a bridge between the local and global behavior of a function.
Okay.
It allows us to connect what's happening at specific points to what's happening over an entire interval.
So it's like saying that the small-scale details of a function somehow reflect the big picture behavior. That's pretty amazing.
Exactly, and this connection has profound implications for all sorts of applications in fields like physics, engineering, and economics.
Okay, I'm really curious now. Can you give me an example of how the mean value theorem helps us solve real-world problems?
Sure, let's say you're studying the growth of a population over time. The mean value theorem can tell you that at some point during that time period, the instantaneous growth rate of the population must have been equal to the average growth rate over the entire period.
So even if the population was growing at different rates at different times, there must have been a moment when the growth rate hit that average value.
Precisely. And this can help you understand the dynamics of population growth. It's just one example, but the mean value theorem has applications in all sorts of fields, anywhere you're dealing with rates of change.
Wow. It seems like calculus is full of these unexpected connections and surprising theorems. It's definitely more than just formulas and equations.
It is.
It's a whole new way of thinking about the world.
It certainly is. It's a journey full of moments,
Yeah.
revealing the hidden beauty and interconnectedness of mathematics.
Okay, so we've explored limits,
Uh-huh.
continuity, and the mean value theorems. Like we've built a solid mathematical foundation.
We have indeed. We've laid the groundwork for understanding the two fundamental operations of calculus, differentiation and integration.
Differentiation and integration, those sound like big, important words. It's time to tackle these two pillars of calculus head on.
They might sound intimidating, but really they're the heart of calculus, and once you understand them, you can unlock incredible insights about the world around us.
Okay, let's start with differentiation. We talked about derivatives earlier, those snapshots of how fast a function is changing at a particular moment. So differentiation is the process of actually finding those derivatives.
That's it. It's like examining a single frame in a movie to see exactly what's happening at that precise moment.
Okay, I like that analogy. But how do we actually find these derivatives? Is there some sort of secret formula or a special set of tools?
There are indeed. Calculus provides us with a whole toolkit of rules and techniques for finding derivatives. It's like learning a new language.
Okay.
Once you understand the grammar, you can differentiate almost any function you encounter.
So it's like cracking the code of calculus. That sounds exciting. Can you give me a sneak peek at some of these differentiation rules?
Absolutely. One of the most basic rules is the power rule. It tells us that if we have a function like x raised to a power, say x squared,
Yeah.
the derivative is simply that power multiplied by x raised to 1 less power. So the derivative of x squared is 2x.
Okay, so we bring that power down in front and decrease the exponent by 1. That seems pretty manageable. What other tricks does this calculus toolkit have?
We have rules for differentiating sums of functions,
Okay.
products of functions, quotients of functions, even compositions of functions. We also have special techniques for differentiating trigonometric functions like sine and cosine, exponential functions, and logarithmic functions. It's a whole world of mathematical tools.
Wow, it sounds like differentiation gives us a superpower to analyze change. But what about its counterpart integration? If differentiation is like taking a snapshot of a function's change, what's integration all about?
Integration is essentially the reverse process of differentiation. It's like taking all those individual snapshots of change from the derivative and stitching them together to create the entire movie. It gives us a way to see the big picture of how a function accumulates change over time or space.
Wait, so if we know the derivative of a function, which tells us how it's changing in each moment, we can use integration to go back and figure out the original function.
That's the idea. Integration is like running the movie in reverse.
Hmm.
It allows us to reconstruct the original function by understanding how its rate of change accumulates.
That's pretty mind-blowing. So differentiation breaks down change into its instantaneous moments, and integration puts those moments back together to reveal the whole story. They really are two sides of the same coin.
Exactly. They complement each other perfectly, giving us a deep and powerful way to understand change.
Okay, I'm starting to see the yin and yang of calculus. But how do we actually go about this process of integration? Is it as straightforward as differentiation with all its rules?
Integration can be a bit trickier than differentiation.
Oh,
While we have some powerful techniques like substitution and integration by parts,
okay.
finding integrals often requires more creativity and intuition. It's a bit more like solving a puzzle.
So differentiation is like following a clear set of instructions, while integration is more like navigating a maze. Why is integration so much more challenging?
It's because with differentiation, we're breaking things down going on the whole to the parts,
Right.
but with integration, we're trying to put the pieces back together, which can be a lot more complex. It often involves recognizing patterns,
Uh-huh.
making clever substitutions, and sometimes even a little bit of educated guessing, followed by checking if our guess works.
Okay, so integration definitely seems to require a bit more finesse, but I imagine the rewards are worth the effort, right? What kind of amazing insights can we gain from integration?
The applications of integration are vast and incredibly powerful.
Like,
We can use it to calculate the volumes of complex shapes,
wow.
to determine the work done by a force, to analyze probability distributions,
Hmm.
to model fluid flow, and even to understand the behavior of electrical circuits.
Wow, it sounds like integration unlocks a whole new level of understanding in so many different fields. But I have to ask,
Yeah.
how does this idea of integration as the reverse of differentiation connect to finding the area under a curve, which is how we first introduced integrals?
Ah, that's where our good friend, the fundamental theorem of calculus, comes in.
Our friend is back.
Remember, it has two parts. The first part tells us that we can calculate a definite integral,
Yeah.
which gives us that area under the curve by finding an antiderivative and then evaluating it at the endpoints of our interval.
Right. It's like a shortcut for finding the area under a curve. Instead of adding up an infinite number of tiny rectangles, we can just find the antiderivative of the function and plug in those endpoints.
Exactly. It's an incredibly powerful connection that makes calculating definite integrals much easier in many cases. And the second part of the fundamental theorem provides the theoretical foundation for this shortcut, solidifying the link between the area under a curve and the antiderivative.
So the fundamental theorem really is the key to the whole calculus kingdom. It connects differentiation and integration, instantaneous and average rates of change, and lets us seamlessly move between the worlds of geometry and algebra. It's like the ultimate mathematical translator.
It is. It's a testament to the brilliance and elegance of calculus, which allows us to capture such complex ideas in such concise and powerful ways.
Well, we've covered a lot of ground in our calculus exploration today, from those ancient Greek paradoxes to the mind-blowing fundamental theorem. It's like we've zoomed through centuries of mathematical discoveries in just a few minutes.
We have, and while it may seem like a lot to take in, remember that we're just scratching the surface. Calculus is a vast and ever-evolving field with endless applications and areas to explore.
It's amazing to think about how calculus has shaped our understanding of the world and continues to push the boundaries of what we know and what we can achieve.
It truly is, and even though we've reached the end of our deep dive for today, I hope this has sparked your curiosity to continue exploring the wonders of calculus.
I know I'm definitely feeling inspired to keep learning more. Thanks for taking us on this incredible journey through the world of calculus.
It was my pleasure.
So where do we go from here? We've laid this incredible foundation of calculus.
We have.
What are some of the really cool practical applications? You mentioned things like calculating volumes and analyzing forces.
Yes.
Can you give me some specific examples that make these applications really come to life?
Absolutely. Let's start with something simple but elegant.
Okay.
Calculating the volume of a sphere. It might seem like a straightforward geometric problem,
Yeah.
but without calculus, it gets pretty tricky.
Okay, I can see that. I remember learning the formula for the volume of a sphere back in geometry class, but I really understood where it came from.
That's where integration shines. By using integration, we can slice the sphere into infinitely thin disks,
Okay.
calculate the volume of each disk, and then add them all up. It's like building a 3D puzzle piece by infinitesimal piece.
So we're basically using the same idea we talked about earlier, approximating the area under a curve with rectangles,
Yes.
but this time we're approximating a volume with these infinitely thin disks.
That's it. And through the magic of integration,
Yeah.
we can arrive at the precise formula for the volume of a sphere. It's a beautiful example of how calculus connects geometry and calculation in a profound way.
That's pretty amazing. It's like we're turning a complex 3D shape into a series of simpler 2D shapes that we can easily work with.
Exactly. And the beauty of it is that this technique can be extended to calculate the volumes of all sorts of irregular shapes, things that would be incredibly difficult, if not impossible, to tackle with traditional geometry alone.
Okay, so integration gives us a powerful tool for understanding volumes. What about analyzing forces? You mentioned that earlier.
Yes.
And I'm really curious to hear more.
Imagine you're designing a bridge.
Okay.
You need to understand the forces acting on the bridge's structure. Gravity, wind, the weight of vehicles crossing it. Calculus, specifically integration, provides a way to calculate the work done by these forces.
Work. Isn't work just force times distance? Like if I push a box across the room, the work I do depends on how much force I use and how far I push it.
That's right. But in many real-world situations, the force is not constant.
Okay.
Think about a rocket launching into space. The force of gravity decreases as the rocket gets farther from Earth.
Okay, I can see how that would complicate things.
That's where integration comes in. We can break down the rocket's journey into tiny segments,
Okay.
calculate the work done over each segment where the force is relatively constant, and then use integration to add up the work done over the entire journey.
So it's similar to the volume calculation. We're breaking a complex problem into smaller, more manageable pieces, then using integration to put it all back together.
Exactly. And this technique of integrating over changing forces has applications in all sorts of fields, from designing roller coasters to understanding the movements of planets.
This is incredible. It feels like calculus is the key to unlocking so many mysteries of the universe. We can use it to understand everything from the shape of a raindrop to the trajectory of a comet.
It truly is a remarkable tool. And what we've discussed today is just a glimpse into the power and beauty of calculus. There are countless other applications.
Wow.
And new ones are being discovered all the time.
It's amazing to think about how this mathematical language developed centuries ago continues to shape our understanding of the world today.
It is. Calculus is a testament to the power of human curiosity and ingenuity, and its impact on science, technology, and our understanding of the universe is immeasurable.
Well, there you have it, a whirlwind tour of calculus, from ancient paradoxes to mind-blowing applications. I have to admit, coming into this deep dive, I was a little intimidated by calculus.
I hear that a lot.
But now I see it in a whole new light. It's not just about memorizing formulas.
Right.
It's a language that allows us to describe and understand the world around us in a truly profound way.
I'm so glad to hear that. And remember, this is just the beginning. The world of calculus is vast and endlessly fascinating. So keep exploring, keep asking questions, and keep pushing the boundaries of your knowledge.
Thanks for being such an incredible guide on this mathematical adventure.
It was my pleasure.
And to all our listeners out there, thank you for joining us in the School of Joy. Class dismissed.